So as a reminder, just a reminder, we covered these locations. In FCC, we will cover these locations in BCC. Also, I want to cover martensite. I think this might be whole another class. So they are very hard material. The drawback is they are brittle. Then we will go to second part of the class, strengthening mechanisms. We will basically cover 4 different strengthening mechanisms. First one is solute, solution, strengthening or hardening. Second one is precipitation. Hardening. Third one is grain boundary. Let's say, yeah, grain boundary. Hardening. One is strain. Hardening. All right, so we have like 50% covered this part. Let me just quickly give you a brief reminder. We said that FCC materials, they are soft materials, and the reason is the slip is very easy in FCC. So FCC, the unit cell of cubic geometry, which atoms located at each of the corners and the center of the cube faces. So do you guys remember how many crystal systems we have? Do you guys remember the crystal systems?
4 hocam.
What's that?
Simple cubic, face-centered, body-centered, and hexagonal-centered.
Okay, this is good answer. Crystal systems. Actually, you guys know we have a unit cell and we have lattice parameters with A, B, C's, and we have some angles, right? We have alpha, beta, gamma in between these 3. Like, let me just draw a ideal unit cell. And lattice constants A, B, and C. And the angles are, we have 3 angles, alpha, beta, and gamma. So the crystal systems are the different forms of this unit cell. Cubic is only one of them. So cubic, we have it once A is equal to B, which is equal to C, and alpha is equal to beta, which is equal to gamma, and they are equal to 90 degrees. Do you guys remember what else we have? What other crystal systems we have?
Hexagonal?
Yes. Hexagonal, great. We have hexagonal. Here we have A is equal to B, and they're not equal to C, and alpha is equal to beta, which is equal to 90 degrees, but gamma is equal to 124. So if you try to 120. So if you try to draw hexagonal, you have to draw something like this. Let me try if I can draw hexagonal. So these are all A's. A is equal to B. We have the bases consist of A's, and we have the height, which is C, correct? So we also have like this kind of representation. Then we will have something like this. Sorry about the bad drawing, but A is equal to B, which is not equal to C, and alpha, beta, 90 degrees, and gamma is 120. What else we have? Let me just tell you. We have tetragonal, right? Tetragonal crystal system. Again, A is equal to B, which is not equal to Z, but all the angles are 90 degrees. Ismail, do you remember other crystal systems?
Hocam, I'm not sure.
Maybe orthorhombic, right? Here, all the lattice parameters are different than each other, but all the angles are equal to 90 degrees. We also have trigonal. Again, the lattice constants are same, but alpha is equal to beta, which is equal to gamma, but they are not equal to 90 degrees. This is again interesting crystal structure. What else we have? Let me just check what did we write? Cubic, hexagonal, tetragonal, orthorhombic, trigonal. Of course, we have monoclinic. Monoclinic crystal system. Again, A is not equal to B, which is not equal to C, but alpha is equal to gamma, which is equal to 90 degrees, but beta is not equal to 90 degree. And I think we only left with triclinic. Here, all the lattice constants are same, but the difference is all the angles are different. Anyways, and they're different than also the 90 degrees. So in this course, in metals, we are dealing with cubic system. And FCC, like copper, silver, gold, aluminum, nickel, or their atoms, they're very soft. The critical result shear stress is very low. They are ductile, but they are extremely soft. So do you guys remember the planes in the unit cell of FCC? What is the main plane?
4-1-1-1.
We have 4 1-1-1 planes, right? We have 4 1-1-1 planes. And what is the slip direction?
1-1-0.
Okay, so each plane contains 3 1-1-0 direction. That is great. That is great. So the Burgers vector is 1-1-0. And what is the magnitude of Burgers vector? The magnitude of Burgers vector. The perfect dislocation is 1/2-1-1-0. So the magnitude should be
1/6 to 1/1.
like apply the Frank's rule. Just apply the Frank's rule.
1/2 hocam.
1/2 or the length of a dislocation over 2. Dislocation over 2. Square root 2, right? We just need to take the square of Burgers vector. Perfect, perfect. So if we know this one, we can conclude the geometry. Like we have an atom here. Plane is 1-1-1 plane. So this is 1-1-1 plane, and the directions are all 1-1-0. These are all 1-1-0 direction. Direction is 1-1-0. So we have 3 1-1-0 direction. And the Burgers vector in FCC is always 1/2-1-1-1, like the perfect edge dislocation and the screw dislocation. How about, so let me just draw another thing. Okay, we have FCC consists of bunch of 1-1-1 planes. So let's continue with drawing 1-1-1 planes. And of course we have families like -1s. Perfect. So let's put an atom here, for example. Let's put an atom. We could have extra atoms, right? We can have extra atoms. So the direction of this perfect dislocation is 1-1-0. Then what is the direction of this guy? This is kind of dislocation. We will have another direction here. So what is the direction of this guy? You guys know what is perfect dislocation. This is the perfect dislocation. It consists of two different two other dislocations. What are these? So this is perfect dislocation. Let's call it PD. So PD can decompose into two different dislocations.
211 hocam. Maybe.
What are these dislocations? Remember it from the previous class?
Shockley partial.
Perfect. These are Shockley partials, right? These are Shockley partials, and the direction is 112, correct? And the length is A by 6, correct? Then, of course, we will have some stacking fault. Like the stacking in FCC goes with ABC, ABCs, right? So let me just quickly draw it again. A, B, B, C, C. So this is C. A, and A. So it is in 2D. You can just go ahead and draw the same representation with such a 2D representation. It will be on top of one another. What I mean is you will have some atoms like this. You'll have some atoms like this. So this is A plane, B is red. So B will be something like this. So in 3D, you will see such a representation. And if we have any missing atom or extra atom or missing plane, we will have some stacking fault. So what if the stacking is changed? By how much energy we require to change the stacking sequence? So what if we change this sequence instead of going ABC, ABC, what if we go with ABC, then B, C, A? So mostly it requires a lot of energy to form stacking faults. But in FCC, the stacking fault energy is relatively low. So in FCC, they mostly have low stacking fault energy. Like the gold is the lowest. Gold is very, very low. Then like silver, then aluminum. It goes to, I don't know which one is the highest in FCC, maybe, I don't know, we have to check. Maybe iridium, I don't know, we have to check. I know iridium has high stacking fault energy, might be the highest, not sure. So in FCC, the stack and fold energy is very low. Then it is simple to create. So if we have one plane and 110, the length is A, let's say A. Perfect, this location, they will decompose with this reaction. So they will decompose into Shockley partials. We will come up with 2 Shockley partials with A over 6, 1, 1, 2. And in between these Shockley partials, we will have some stack and folds. So if you apply the Frank's rule, A over 2, let's normalize them by A. So 1 over 2, 1, 1, 0 will decompose into, 1 over 6, 2, 1, 1, right? The perfect dislocation will decompose into 1 over 6, 2, 1, 1, plus 1 over 6. What should be the rest? 1 over 6, I think 1, 2, minus 1, correct? Plus the stack and fold energy in between them. So gamma is the stack and fold energy. So if this stack and fold energy is too high, this reaction cannot happen. But in FCC, the stack and fold energy is small. Then it is very favorable to happen. But in BCC, you may not see this reaction happening. So the stack and fold energy also depends on how wide is this separation distance. So stack and fold energy is too high when we have no splitting. Any questions so far?
No, hocam.
So do you guys remember until this point?
Yes.
Perfect. And do you guys remember all right, so if we have such a representation, so for Shockley partials, we have screw component and edge component. We have edge component and the screw component. So I will send you an homework, or let's discuss it all together. Let me open a new page and ask you the question. Let's call it simple quiz. Maybe we can or let's call it an in-class assignment. So let me just try to draw. You know the screw part and edge part, and you know how we have splitting. So let's say calculate the formula or the expression of force between the Shockley partials of a perfect edge, or let's say screw this time, screw this location. In FCC, when the separation distance is, let's say, D, when they are separated by the distance D. So please think about what should be the approach, how we can deal with it. Ismail, do you have any idea?
Hocam, I think we will use the vectors. So we know
Good.
1, 1, 0 vector in the edge of the system.
Mm-hmm.
So probably, I'm not sure what the edge force is then 1, 0, 0.
Yeah.
0, 1, 0. I'm not sure. Is it X direction or Y direction? And
Perfect. You have to use the approach of vectors. So you need to first draw a perfect screw dislocation, then decompose it into two main parts, edge and screw parts. Then you'll just need to apply the pitch collar force formula. Please try to do it by yourself first. Then I can show you some hints to you. Don't forget when they split. So if this is a dislocation, where is the Burgers vector? Burgers vector is along dislocation line, right? So this is the Burgers vector direction. And which one is the tangent vector? For edge, they are always perpendicular to one another. So Burgers vector is this guy right here, 1/2, 1, 1, 0, and the tangent vector is this guy right here for edge dislocation, 1, 1, 0. So think about this question. Ismail, your approach is pretty accurate. Try to start with it. So dissociation of the perfect dislocation on 1, 1, 1 plane. You just know the reaction. Reaction is very simple. 1/2, 1, 1, 0 will go into, so it's basically this formula. And the Burger's vector of perfect dislocation will be equal to Burger's vector of first Shockley partial plus the Burger's vector of second Shockley partial. And all the Burger's vector needs to satisfy, so the Burger's vector of partials or perfect times the normal, the dot product, is equal to 0, or the Shockley partials, any Shockley partial. Normal vector should be equal to 0. What I mean is we will have a Burger's vector of perfect dislocation, which decompose into Burger's vector of first Shockley partial plus the Burger's vector of second dislocation. And what was the magnitude of this guy, perfect dislocation? Do you guys remember the magnitude of perfect dislocation?
Dislocation over 2 times square root of 2. Is
So
it?
A divided by square root of 2. And the Shockley, how about the Shockley? The magnitude. So first one is equal to the second one. Let's write this way. Which is equal to, can you guys tell me the magnitude? Do you guys remember it is like 1/6, 1, 1, 2. So can you calculate the magnitude of it?
Hocam, can I ask some question?
Can you please try to calculate the magnitude of this Burger's vector? Ismail?
Hocam, actually, I'm not sure how to calculate. Is it like
Just the magnitude is nothing but square root 1/36, 1 plus so it will be like 1/6 square root of 6. So it is a square root of 6. Just magnitude, it is not a big deal. So any question so far?
Yes, hocam, I have one.
Yes, go ahead.
For the Burger vector, we said the magnitude is a over square root of 2, but for the beginning, you said a over 2 times square root of 2.
All right, please try to calculate the magnitude of this guy. Tell me what is the magnitude of this one?
to square root in square 2 over 4. Basically 1 over 2.
Tell it again.
1 over square root of 2.
So 1 over 4, if you take the square root of this guy, times 1 square plus 1 square plus 0 square, correct? Which is equal to 1 over 2 square root of 2a, right? Is it correct? And what happens if you just divide square root of 2 and the square root of 2? You will just come up with square root of 2 here. Is it correct, or
Okay.
I'm doing some wrong in math?
Confused.
Any question? So did you guys all understand the magnitude of Burgers vector?
Yes, hocam.
Yes, hocam.
Okay, so in the question, was it edge dislocation or screw dislocation? I totally forgot. Let's go back. Screw dislocation, okay? So in screw dislocation, is the Burgers vector parallel to the tangent vector, or they are perpendicular to each other?
Perpendicular.
So edge dislocation, the Burgers vector is perpendicular to the tangent vector, but for screw dislocation, they are parallel to one another. So the dissociation leads to, we will have one here, one here, and the tangent vector is this, guys. So we will have both edge components and screw components. And the angle is just 30 degrees here. It's 30 degrees. Then you can find these components as just a square root of 6, which is this guy, times the sine 30. And the other component is a square root of 6 times the cosine 30, which is equal to a, so sine 30 is 1 over 2, right? And cosine 30 is square root of 3 by 2, a square root of 3. So what was the cosine 30? Is it square root of 3 by 2?
Yes,
Ismail,
hocam.
is it correct?
Yes, hocam.
Then we will come up with, I'll just decompose this and we will have something like this, a divided by 2 square root of 2. Then we need to set the geometry to calculate the pitch collar forces. So we have edge components which attract each other. Then we have screw components which just repulse each other. So let me just go to the next step and leave it to you. We have edge component, let's write edge. Attraction. Tangent is, of course, perpendicular. This time, tangent vector. They attract each other, and the separation distance is d. And Burger's vector is a for the edge component, 2 square root of 6. Then you just need to find the tangent vector, Burger's vector. Then, like we have to T1, Burger's vector 1, then T2, Burger's vector 2. You just need to write these. Then using this, you can find the attraction force of H. Using, of course, the stress field of the edge dislocation. For the script part, by the way, maybe let me just tell you what is the tangent vector of this guy. It's along Z, so 0, 0, 1. The second tangent vector is same. Again, 0, 0, 1. And the Burger's vector is along X direction. We will have H Burger's vector 0, 0, then minus BA 0, 0. I'm pretty sure you guys know the stress fields of the edge dislocation. We have sigma XX, sigma YY, and sigma ZZ. And we have tau XY, tau YX. Then the rest is basically 0. Then multiply it with this guy. Zero, 0 times, I'm just applying the peach color force formula, times this guy, 0, 0, 1. And do you guys remember what is sigma XX and what is tau XY? So if we have a edge dislocation, it has a stress field itself. It has some compressive stress fields and tensile stress fields, correct? And also we have some shear stresses on XY. Do you guys remember this? Maybe you can just go ahead and Google what is the stress field of edge dislocation. Can you Google it for me? You should have some formula, which is a function of shear modulus and 2 pi. I think it should be something like this. 2 pi 1 minus Poisson's ratio. Can you guys please try to Google, just try to Google the stress field of an edge dislocation, and let's solve the question all together. Who can help me to find the stress field of an edge dislocation? Resul?
Hocam, I'm Googling right now. For example, sigma XX, like it says 0. For sigma YY, it says 0, and etc. But
are you sure if you're checking edge dislocation, not screw dislocation?
Okay, hocam, let me check again. It says straight dislocation. Is it the same with like edge dislocation hocam?
Who came up with the formula of an edge dislocation stress field?
Should it start with the tie, and then there's the d over 2pi, 1 minus the Gaussian ratio?
So is sigma xx this guy? Let me also go ahead and check. You guys should know the stress tensor of both edge dislocation and screw dislocation. Edge creates a tension, compression, but screw only creates the shear stress. So let me just quickly go ahead and check this. Ismail, did you find the stress field of an edge dislocation? Ismail?
Hocam, I found something, but I'm not sure.
Why don't you just Google it, the stress field of an edge dislocation? Okay, the first link. We have covered it in the first class though. You guys should know the energy and the stress field of an dislocations. All right, let me just write what I came up with. Sigma xx is equal to minus some constant, and this constant, I'm pretty sure it is just g b 2 pi 1 minus Poisson's ratio minus d y, the coordinates 3x squared plus y squared, x squared plus y squared square. So if you have an edge dislocation and if you have your coordinates with x and y, you can calculate the corresponding stress field at that location. Then sigma yy is nothing but dy x squared minus y squared, x squared plus y squared square. Then sigma xy, which is equal to sigma yx, which is equal to dx x squared minus y squared divided by x squared plus y squared square. So we have the stress field formula. You just need to put this stress field into this equation. Then you will come up with the, let's deal with here first. What we gonna come up, let me just check. This guy times this guy, sigma x times Berger's vector of an edge dislocation. So I'm taking this and multiply it with this. We have 0, 0. Then this guy times this guy, which is tau yz times minus BA. Then the third column is basically 0. Then 0. Oops. Yeah. Then you just need to multiply it with 0, 0, 1. Then we will come up with what we're gonna come up. So we will come up with basically this guy right here, minus tau xy BA. Then this guy right here, sigma XXBA, but this is climb, so we don't allow climb. This is climb. We don't need any climb, no climb allowed. Then 0. Then you just need to find this guy. We only have this one, tau xy, and let's check what is tau xy. I don't care about this part. I do just care about this part. So it will be only this guy right here. And if we have a separation distance of d, so I'll just multiply it with b. So we will have b squared because we have another b right here. So FH, this is for attraction, will be minus G or mu, whatever you call it, minus G or mu. I prefer to call it by mu. G B times another B makes it B squared divided by 2 pi 1 minus Poisson's ratio times the separation distance, and the other terms are basically 0. So this is attraction. Then for the script force, you need to follow the same procedure, and you guys can find the repulsive terms too. I'm not gonna repeat same thing to calculate the script part. Basically, where is the question? You guys go ahead and calculate the effect of script part. Then maybe the question could be like the optimization of D value. For example, sorry, I reached the maximum numbers of pages. So the question could be the obtain the expression that gives the ideal, like that gives the optimal ideal equilibrium distance D between two partial dislocations for a generic stacking fault energy. Like to calculate the generic stacking fault energy, what should be the D value? Then you guys need to just use the generic stacking fault energy formulation, which is like FR is equal to D ER X dx. Then you need to equate it with stacking fault energy. Then I think you guys can find D value. Maybe as a homework, you can solve it. So any questions so far?
Hocam, may I ask what is ER?
ER is the energy. The energy is proportional with alpha, some constant times B squared. Like if you remember the Frank's rule. Frank's rule. So this is Frank's rule, basically alpha times B squared. Any more question? So for this course, I'll stop at this point. Let's take 10 minutes break and continue after the break. All right, so there is another very important concept. I think the only one we left is Thompson tetrahedron. We'll just go with the PowerPoint. So we have covered these parts. So let's remember, is the lattice resistance in FCC high or low? Anyone? The lattice resistance in FCC, is it high or low? Please, guys, help me here.
It must be low.
It is low, right? They move very easily. How about stack and fold energy in FCC?
Low as
than the other.
All right, so we know till this part, and we will cover also Thompson tetrahedral and dislocation junctions in FCC. So in FCC, we have 4, 110. Sorry. Can you guys see it is? I want to just make it bigger, like the full scene. Anyways. Okay, so the main plane is 111. We have 4 111 plane and 3 110 direction. Okay, these are the directions. 110 directions and 001, 010, 100, and the plane is 1 plane. And in FCC, we have 12 subsystems, and the second sequence is just ABC. The lattice resistance, the definition is due to the necessity to make and break bonds at the core of the dislocation every time it moves an atomic distance. So it is called as also peerless stress, peerless barrier. So the lattice resistance is very low in FCC. Perfect. So perfect dislocation, we have Berger's vector, transitional vector. It is as small as possible. For partial dislocation, we have no transitional vector. So here, which one is the perfect dislocation? This guy right here, right? Then these two are the partial dislocations. Basically, the Frank rule suggests that constant times G times B square will give us the energy of dislocation. And the energy of dislocation is just proportional with B square. So once we have any edge or screw dislocation, perfect dislocation, they dissipate into some partial dislocations. We have Shockley partials and Frank partials. The Shockley partials, they just form by splitting a perfect dislocation. Instead, Frank partial, they form by inserting or partly removing the 111 plane. So this is the 111 plane. Basically, the Shockley partials are very mobile dislocation. And the definition is 1/6, 112. And the Frank dislocations are immobile dislocations. And the definition is 1/3, 111 dislocation. So if you go ahead and check edge dislocation, decomposing into 2 parts, the reaction is this one. If you compare the energies, just you need to find the energy of this one, and this one. And if the energy of the summation of these guys is less than the energy of this one, of course, we will have some breakage. We will have some decomposition. Of course, here we also have some Stekenfold energy. Then you can also add the energy of Stekenfolds into your energy calculations. So these are all energy calculation. So here we can add some Stekenfold energy term. All right, so we know that in FCC, this is favorable. So who can calculate the energy of this one? Ismail?
Yes, hocam.
Can you calculate the energy of the perfect dislocation?
Hocam, if you normalize it, it is 1/2.
1/2 you are suggesting, because we will have 1/4 1 square plus another 1 square. I mean, you guys know the idea, and the other part will come up as 1/3, and we will see this is energetically favorable. All right. Can I delete these drawings? Let me check. Annotate and clear my drawings. Okay. So once we calculate the energy, we get 1/2 and 1/3. Clearly, 1/2 is greater than 1/3. Thus, there is a decrease in energy, and the splitting of the dislocation is favorable energetically. Shockley partials, we know the Stepen sequence. We have A type of 1-1-1 plane, B type of 1-1-1 plane, C type of 1-1-1 plane. And the Shockley partials just splitting of this dislocation into two main partials. And we know that this is energetically favorable. And while creating these Shockley partials, we always create these Stekenfolds. This is very important, guys. We have Stekenfolds once we create the Shockley partials. The second fold is here, for example. ABC, ABC, then we have AC, AC. So this is Stekenfold. We also have some Stekenfold energy. So here you can have some graphs. You can take a look at them. I'll just post this one. Stekenfold energy, the formula is just G, shear modulus, times the B2 times B3, which are the Burgers vector of partial dislocations, divided by 2 pi d. So once we have edge dislocation or screw dislocation, basically they deform with edge dislocation, not screw dislocation. So forget about screw dislocation right now. Once we have edge dislocation, they decompose into two main parts. And the Burgers vectors are these guys. And the Burgers vector of edge dislocation is this Burgers vector. They decompose into these two green Burgers vector. Then in between these Shockley partials, we have Stekenfolds, don't forget. Yeah, if the spacing of the partial is d, the repulsive force per unit length between the partials of pure edge or pure screw dislocation. For pure edge, we just derive it. It's related to GB square. For pure screw, I think you can calculate this on your own. Then pure screw, it is GB square 2 times 3V divided by like this formula. Please read the homework and understand it. here I want to just charge my iPad. Shock the partial dislocation, this taken fault energy will rise widely from metal to metal depending on the width of the fault. What I mean is we have a plane, 1-1-1 plane. We have edge dislocation, decompose into two shock the partials, and the taken fault energy depends on the separation distance between these D. The width of the taken fault in copper is 10 atomic spacing. In aluminum, it's only 2 atomic separation. The copper is very low because D is very high. And aluminum, the taken fault energy is around 200 pi. That means very high taken fault energy. Gold is very, very low. So if we have its separation distance, D is equal to 0. Like if we have D is equal to 0, we have very high taken fault energy. That means taken fault is very, very low. Taken fault energy and taken fault is just inversely proportional. Let's clear all drawings. So the width of taken fault is the consequences of the balance between the repulsive force between two partial dislocation and attractive force due to the taken fault. So when taken fault energy is high, of course, the energy of the other term, which we have it. Here, right? Let's check. Yeah, we just add taken fault energy to this reaction. If the taken fault energy is high, this reaction is not favorable. But if the second, because we are adding the taken fault energy to this part, if it is low, of course, it is favorable. All right. Let's check what else we have here. Shock the partials, okay. So in between shock the partials, we always have some taken faults. For example, here we have shock the partials and the shaded area is taken faults. Frank dislocation, we have taken faults. Here you see the taken faults. So these are all TEM images, and once you look at the TEM images, here we have edge dislocation, decompose into shock the partials, we have taken faults. Frank dislocation, in between them, we have taken faults. So in reality, if you check the TEM, you will see taken faults. Row out, do you remember the cross slip?
Yes, wasn't it the mix between SP and SR dislocations, right?
Perfect. So once we have another 1-1-1 plane, the dislocation will want to go to another plane, but shock the partials cannot go to the other plane. Instead, here we have two shock the partials. They came into each other, and this part, the perfect dislocation, moves to another plane, and the sequence of events during the cross slip is here. Formation of screw part, we have screw part here, and don't forget, edge dislocation cannot cross slip. Only screw dislocation can cross slip, and this screw part go to the other plane again. decomposed into two parts, and this is called screw dislocation. Thompson tetrahedron. This is very, very important. So once we said we have 4 1-1-1 planes. Once we combine all the 4 planes on top of each other, we will have this Thompson tetrahedron. So once we combine all the planes, we come up with a tetrahedron. Here, the Greek letters show each plane. So each Greek letter is one plane. So this representation is very important, guys. So the Greek letter represents 4 planes: alpha, beta, gamma, and kappa. And for example, AB is the direction of gamma plane. Let's check with the AB. So this is the direction in gamma plane. So here we have the Thompson tetrahedron, different planes, and here you see perfect dislocation. For example, along 1-1-1. Here we have the plane. So this direction is 1-1-1 direction. Let me draw it for you. So this direction, for example, is 1-1-1 direction, or this direction is 1-1-1 direction, or this direction is 1-1-1 direction. But always you can decompose your perfect dislocation into 2 main Shockley partials. For example, here we have splitting 2-1-1. For example, here we have splitting. This is Shockley partial, another Shockley partial, which gives you the full 1-1-1. Sorry, 1-1-0, not 1-1-1. This is 1-1-0. Perfect dislocation. So this is the representation. We have Greek letters and we have full letters. So the corners of the tetrahedron denoted by A, B, C, D. So if you wrap up all the 4 planes, we come up with alpha, beta, gamma, and kappa planes in one tetrahedron. So this formation is very real. If you check, annotate again. So from A to B, we have perfect dislocation, but from A to kappa, we have Shockley partials. Kappa to beta, we have Shockley partials. So Shockley partials can be represented to line the corners to the centers of the face, from letter to Greek letter, from capital letter to Greek letter, we have Shockley partials. How about frank dislocations? So they just form by inserting or removing the 1-1-1 plane. So we have some ABCs, and once we remove this plane, we will have some frank dislocations, and the frank dislocation, so they exist in FCC and HCP. We have positive frank dislocation, depending on the size of the Berger's vector, like the irradiation damage. If we have too much irradiation, like dislocation density is incredibly high, and we have positive dislocation. And if the frank dislocation is just as opposed to the Berger's vector sign, we have negative dislocations. And I'm sure you guys remember the Lomer cut rules. Once we have 2 different planes, And the edge dislocation decomposed into two Shockley partials. Once these Shockley partials came together at the junction, which is called as Lomer-Cutwell junction, they create the stay-rod dislocations. These are the stay-rod dislocations, and the energy is very favorable. That is why we see high hardening in FCC. I just want to clear this drawing, so I clear all my drawings. So this reaction is very energetically favorable. If you just, I think we covered it in the previous class. And this is just a summary. Shockley partial, we have 1/6, 112. And the Shockley partial is from ladder to Greek. Stay rod, again, 1/6, 110. Partial dislocation, positive and negatives, 1/3, 111. Perfect dislocation is 1/2, 110. Strength of a junction, I have a table, so Lomer-Cutwells are very strong junctions. You can check the energy of this dislocation and check if it is energy favorable or not. You will see that Lomer junctions are very energetically favorable. I always wonder the formation of this second fold tetrahedron. So I always felt like, okay, in theory, looks fine, looks promising, but how about in general, like in reality? So we have performed some discrete dislocation dynamic simulations, and I want to just share the results of this discrete dislocation dynamics simulations. Let me just open one. Here is it? I have to find my movies. It's here. All right. So based on the go ahead and show it to you. Okay, let's start from the beginning. We have these points, then energetically we will lose energy from the corners. Then we create this tetrahedron. So we really have this French dislocation formation in reality. So again, I wanna spend more time on this Thompson tetrahedron. This is extremely important. In FCC, you have to know which dislocation is which dislocation. So here we have some Greek letters, some capital letters, some corners. Actually, let me just share a whiteboard. Don't remember this. This is the whole combination of 4 different planes. And let me just open my MacBook. Share a whiteboard with you. And try to discuss all together. Thompson tetrahedron. This is very, very important. Whiteboard, okay. First, perfect dislocation. Do you guys remember how we see the perfect dislocation in the Thompson tetrahedron? It was from capital letter to capital letter, right? It was from capital letter to capital letter. For example, AB or AC. All these dislocations are perfect dislocations, or DC, right? Any capital to capital are perfect dislocation. Glide planes, the planes, let me also write the definition of glide planes. Glide plane. The planes are always Greek letters, gamma and kappa. So these are Greek letters. Then, do you guys remember the representation of Shockley partials? What was the representation of Shockley partials?
It was from
Roa?
the capital letters to Latin.
Perfect. So it is from capital letter to Greek letter, right? So if you remember, let me just draw just only one plane. Capital A, alpha, beta. This is perfect dislocation. Alpha, A to alpha, or alpha to beta. So Greek to capital is also Shockley partial. They give us the Shockley partial. That means AB at any phase, let's say this alpha phase, alpha plane, is equal to A alpha plus alpha beta. This is the representation of two Shockley partials on the alpha plane. How about stay rod dislocation? Stay rod. So stay rod is just the bridge that connects two glide planes inside the tetrahedron. So can you guys find what is so? Firstly, to find the stay rod, we need to combine two Shockley partials, correct?
Yes.
Yes, sir.
So once you combine two different Shockley partials, what you get is from Greek to Greek. So stay rod is just Greek to Greek. So for example, alpha to beta. Alpha, beta is the stay rod, or beta, gamma is the stay rod. Lastly, we also have, what was the other type of dislocation? What is the other type? I'm sure you guys remember. How can I add new pages? I always have some difficulty. Oops. Oops, I can't find how to add a page, sorry. Just turn it. All right. Here you go. We have Frank dislocation, right? Frank dislocation. This is interesting. So this is from letter to Greek, but it should be inside the same plane. For example, A to alpha, or B to beta, or C to gamma, or D to kappa. To kappa. So should be always inside the same plane. So if you draw the whole, is Mehmet Baltacıoğlu here? Mehmet, are you here? I think he's not okay. Here we have 4 planes. Oh, let's say this is beta, this is alpha, this is kappa, and this point is gamma. And that's A, B, C, and the rest is D, D, D. Okay, which dislocation is this guy right here? Which dislocation is this one right here?
Shockley hocam.
Is it Shockley?
I think so.
So let's firstly draw AB. Let's firstly draw AB. This is full dislocation, right? Let's go to representation. Capital to capital is perfect dislocation. AB so this can be the combination of, let's check, either perfect dislocation is the combination of either these two or these two, right? These are all Shockley partials. So the Shockley partials of AB can be A to gamma plus gamma to beta, or A to kappa plus kappa to beta. So show me one stair rod dislocation. For example, Greek to Greek is the stair rod. This guy is the stair rod, and it's just center of plane to another center of plane. And it doesn't belong to any plane. So it is just immobile. This is not mobile dislocation. It is immobile dislocation. How about frank dislocation? Please show me one letter to Greek or Greek to letter. For example, this guy here, right? Gamma, where is gamma? This one is the frank dislocation. And again, it doesn't belong to any plane.
Hocam, can you show it again?
Of course. Sorry.
Just the last part, the frank part.
Right. I just want to clear this. So it will go from either C to gamma. So it doesn't belong to any plane. Don't forget, it doesn't belong to any plane and can be mobile or immobile. Or let's check this guy right here. Or this one right here. Or this guy right here. These are all frank dislocation, any D to the center of all. So actually, that's basically it, but I just want you to find, we have 4 distinct frank dislocations, right? We have 4 distinct frank dislocations. So let's solve an example. So we have, let's say, this is 1, 1, 1 plane. We have two perfect dislocations, A to B, and let's say B to D. Then they will split, right? They will split eventually. We will come up with two splitting, two Shockley partials. And the Shockley partials are from Latin to Greek, for example. Let's call it with, we are on the gamma plane. Gamma to beta this time. This one will also split. So let's say this is BD. And we are on the gamma plane again. We will have some B gamma and D gamma Shockley partials, right? B gamma and gamma D Shockley partials. So once the perfect dislocation combines, for example, these two, AB plus BD, what we're gonna get? So if we have AB here and BD here, so this is A, this is B, AB and BD here. Let me just draw it again. A to B, and this is B to D. We will come up with A to D, right? A to D. So how can we come up with A to D? Once all of these Shockley partials combine, A gamma plus gamma beta. By the way, guys, are we recording the class? We are, right? Perfect. So this is first dislocation. Then we have the second dislocation, perfect dislocation, gamma D. Then they will just clear each other. What we're gonna left is these two guys. Then at the same plane, A gamma plus gamma D will give us A D. So this is just the dipole in the same direction, same Burgers vector. Then they annihilate each other. Gamma beta, beta gamma. They are just dipole of the same dislocation, same direction, same Burgers vector with different sign. So same with different sign. Then they just annihilate each other. So this is just then like internal fault. This is just then another type of intrinsic fault. It's not like the external fault, it's kind of internal fault. All right, so how we can create stair-rod dislocations? For stair-rod, we have first plane, another plane. We have two Shockley partials. So here, let's call this is an gamma plane, this is an alpha plane. And let's say this is B, D. Here, it's gamma plane. We have gamma beta, here another, because it splits into two Shockley partials, A gamma and gamma beta. The first perfect dislocation was AB. Here, let's say we have BC dislocation. They will decompose into B. The plane is alpha plane and alpha C. Then these two dislocation will combine. Gamma beta plus beta gamma. Then we will have gamma alpha, which is stair rod. And we said the stair rod is, where is it? I like turn it this way. Yeah, stair rod is from Greek to Greek. You can create the formation of stair rods. How about Frank dislocation? Can you explain me how can we find the Frank dislocation?
It was Latin to Greek or Greek to Latin, right?
Perfect. So Frank is just the combination of stair rod and the Shockley. All right, I wanna go to my other page. Guys. Sorry, my battery is only 1%. So I will stop at the formation of Frank dislocation.
Hocam, we can't hear you.
Sorry, guys, can you hear me?
Yes, hocam.
Yes, hocam.
Okay, the battery of my tablet is dead. So I'll stop at this point at the Frank's dislocation. Just wanna ask, is it clear? Do you have any questions so far? So Roa, do you have any question? Was it clear for you? The Thompson tetrahedron?
Yeah, that was clear. It's just the force calculation part was a bit tricky.
Oh, yeah. Maybe, yeah, you guys can solve the homework problem. And I think we are done with dislocations in FCC. So which dislocations, Roa? Please summarize me. What are the dislocations in FCC?
We have the perfect one, the Shakely one, and Frank. And the last one is, I can't remember.
Right.
Yeah.
From Greek to Greek is the stair rod. Letter to letter is perfect. Letter to Greek is Shockley partial, and the Frank is only letter to Greek, but on the same plane, A to alpha, for example. Ismail, any question?
No, hocam. Hocam, may I ask which book are you following?
There is a book written by Hertz and Bacon. It's called as Introduction to Dislocation. It is Hull and Bacon.
Okay, hocam, in first lecture, you said the theory of dislocation.
I think Introduction to Dislocation.
And that book was... Okay, hocam. Thank you.
It's in the syllabus, yeah.